Okay, so this is the lecture of the 30th of March, I'm sorry, and which I am, as you can see, taping one day late, but anyway, I thought as I was preparing the class, following from last time, that maybe it would be appropriate to do a little bit of a I don't know, review for some, perhaps it's the first time for others and so on. Let's say a brief passing through the landscape of random variables and so on, just so that the language that I'm using is not foreign in case that you haven't dealt with this material before. So in this first segment, which I'm going to take now, I'm taking just one minor step back and just produce a review and then of this random process, random variables and so on. Very, what do you say, minimalist. But once I finish doing that, then we will retake our objective, which is of course to provide you with these techniques for damage detection and so on that we can use in structural health monitoring. In the previous class, of course, I did novelty detection, I believe, and we talked about the chi-square distribution and so on. So let me begin. Item number one here. What I've got here is just a listing of the subjects that I plan to discuss. So let me start by just refreshing our memory with regards to some definitions that we used last time. So here are two distributions, right? Probability distributions of a certain variable. The variable, we're going to call it x here, but of course it could be, if you want to think in very physical terms, that could be, let's say, the frequency of the fundamental frequency of the structure, for example. Because there is noise and because nothing can be computed with exact precision and so on, that frequency is not a number. It is actually a random variable with some distribution. So if this is the reference state or undamaged, we would expect that reference state to have some mean, right? The mean of the reference state. And if there is damage, depending on how big is the damage and how much is the sensitivity, we would have that distribution shift, right? And in the case of frequencies, we would expect it to shift to the left, and we would say that there is some sort of mean damage, right? Frequency. That is, if we did this test 1 million times, when it was not damaged, we'd have something like that. And if we did the test 1 million times after the damage took place without changing it, maybe we'd have something like this. Of course, we actually don't do that. We don't have those million tests. This is just to describe the concepts. Now, if we take this value here as our critical separation, and we decide that anything to the left of that we are going to call damage, then we would say that this area here is the type 1 error, because we would say that if x is found to be less than xc, we would announce damage, right? We would announce damage, and that if x is greater than xc, we would say the system is in the reference state. Now, the type 1 error then means that the system could be on damage, right? But you could get a value here, because there is some probability that the value of x is less than xc while the system is still on the reference state. So if we had an idea what this is, and in principle, at least in principle, we could generate this curve, right? Because we could repeat the test for a full year, 2 times a day, and so on. We could have enough data to get an idea of what this curve looks like. And here is our XC. So the type 1 error is the probability that we would dictate that the system is okay when the system is actually damaged. I'm sorry, take that back. No. If we find the value here, we would announce that the system is damaged, but the system may be okay. So this would be false positives, right? So the type 1 error is false positives, right? Now, depending on the damage, then we would have this curve. As the damage gets larger, it shifts to the left, to the right, and so on. But once we decide on the XC, of course, this curve we really don't have, because we're not really going to test the structure a million times after the damage took place, right? But we can think mentally that it does exist. And since our criteria is to call damaged things to the left of XC, we can see that there is a possibility that the system is damaged and that we would say that the system is not. Meaning things that are on this side of XC could be on the distribution of the damaged state too. And that area right there is what we call the type 2 error, right? So whatever is on the right of the type 2 error, that is this area, on the damage distribution, this is just 1 minus the type 2, and so that's what we call the power of the test, right? So the power of the test is the probability that if the system is damaged, we would announce it to be damaged. For example, if the type 2 error, if the type 1 error is 5%, which we said from this curve, and it happened to imply a 20% of the damage distribution being on the right, then we would have that for that particular damage, we would have a power of the test of 80%. Okay? So the type 2 error is what we call false negatives, right? So that means that the system was actually damaged. We get a test over here. We say that it's fine because it's to the right of XC, but in fact it was damaged, right? All right, so that's the quick review regarding, power of the test, type 1 error, type 2 error. Now, we've been talking about things like probability distributions and so on, so I guess it's worth saying that, of course, we're always talking about a random variable, right? So what is a random variable? You would think, intuitively it's kind of clear for us, right? A random variable is something you think intuitively that you just can't predict, right? You don't know what it's going to be. If you really want to be if you want to go to a formal definition, then we start running into subtleties, because randomness in itself is kind of a subtle issue, right? If there are physical laws that govern how things respond to any stimuli or any cause and so on, then what do we mean by random, right? Not knowing something doesn't necessarily mean it's a random, right? For example, let me give you, not that I want to go into the philosophy of the thing, but let me give you the thing. If we throw a coin up or down, right? It's heads or tails. So we say that process is random, right? Because we don't know what is going to come out. However, if you said, let me make a mathematical model of the coin, let me make a model of the finger that's flipping the coin, of the air and the resistance of the air and so on, and then you go like this, you can track you should in principle track what that coin is going to do, and therefore whether it lands heads or tails is not random. It's a function of how you flipped it with your finger and how you did this and that. So almost any process except at the level of quantum mechanics, if you want to go that deep, is basically deterministic in the sense that we say that there are some laws that govern the evolution. Now, in many cases, the number of things that govern what's going to happen is so large and is so out of our control that we give up basically and say, well, that effect that we're going to look like tossing the coin is random. Meaning I don't really have any way to really predict what it's going to be, even though I realize that something is determining it, right? So this is, I won't go into defining a random variable from a formal point of view. I will just say we have an intuitive understanding of randomness. Now, a random process is a family of random variables. Okay? A random process is basically a family of random variables. We could say that the generation of earthquakes in California is a random process, right? Meaning that every time, we don't know when it's going to happen, which fault is going to be the one, whatever. You know, if there, even if we look at San Andreas fault, we can say that there is a certain probability that there would be an earthquake of a certain size on a certain day and so on. And when that earthquake occurs, then we measure a realization of the random process, which is the actual measurement of the earthquake at some location, right? So a random process is a family of random variables, and here comes the first thing that is quantitative, which I have used, stationarity. So what do we mean when we say that a random process or a random variable is stationary? Well, this is the first thing. Let's say that this is x and this is time, right? And if you want to think in terms of specifics, think that that is the motion at the base of this building during some earthquake, right? So we can say that's not random when we look at it, right? Because we know what it is. But we can assume that that is the realization of one realization of a random process, right? This is the one that we observed. However, you can imagine in your head that it could have been different, right? It could have been different. And in fact, it could have been different again and again and again and again and again. So if we take a given time here, let's say t1, and you look at the value of the variable in this realization and this realization and this realization and this realization, then that variable will have, I'm going to draw it with a given mean, but that variable could have some sort of a PDF, right? Let me give you another example that might be even better than the earthquake, because the earthquake is one that we don't, we don't get a million earthquakes and so on, so it might be perhaps a little bit more abstract. Think about it this way. Let's say that you have your car, and that in your car you put a sensor in the windshield, and you ride on a road 5 miles. Okay? And that sensor, while you're riding, is recording the accelerations there, and so you get that signal. So let's say that that signal is what that accelerometer picks up as you drive those 5 miles at 20 mph. So you're going 20 miles per hour for 5 miles, and your accelerometer measured this. Now imagine that you just go back and do it again, and you go back and do it again, and you go back and do it again. You can do that 100 times, right? You're riding in the same road at the same speed from one point to the other. you know that when you look, the signals that you would record here are not the same, right? They're not the same. There is enough randomness in the process of the roughness of the road and so on that you will not get the same realizations. Now, if we take a look, let's say when the car was here, at this position, maybe sometime from start, and you look at all the values that were measured at that time, we are looking across the ensemble, right? This is the ensemble of all the possibilities. When you're looking down, you will have one value here, and if you plot them all together, there is a PDF for what's happening at time t equals to t1, right? Now, if we now go to t equal to t2 here, and we do the same thing, notice that I'm not averaging along the time. I am averaging across the ensemble. So, I'm not averaging, I'm inspecting across the ensemble. So I go to T2 and I read what my sensor was measuring at that time, right? From my 5,000 runs of this 5 miles of road. And I will get, at that time, different values than the original one, but when I plot the PDF, I may find that the PDF is the same. For all practical purposes, I would need to do infinite to know, right? But let's say here that at t equal to t2, these two things are the same. So if the probability distribution at various times during the random realizations or in the random process is the same, then we say that the process is stationary. Right? That is, the process is not changing with time. It's obvious that a stationarity is an idealization, right? Because stationarity means it's not changing with time at all. But in reality, when you start with your car here, you're at 0, right? It takes you a few seconds to go to 20 miles per hour. And by the time you have to get here, you have to stop the car. And so you actually are not going 20 miles an hour at the edges, right? And you might see that the statistics at that point are different than the statistics other than in that end segments. But, you know, leaving those details out, and you could obviously take a segment of the signals, forget the beginning, forget the end, you can say that the process is stationary because the probability density at any cut that you make is the same. Notice that one thing that I want to emphasize here is that when you talk about random variables, you have to teach your brain not to think always in terms of you're looking at one signal. Because when you are talking about a random variable, like that ride that I'm talking about, you may have done that ride once. And so you just have that one that you did. But you have to think in terms of the fact that you could have done that many times, infinite times, and that when we are talking about the mean, we're not talking about the mean to the right. We're talking about the mean at a given time of all the possible realizations that could have occurred. And at another time, again. And we're talking not only on the mean, but the variance and, in general, of the probability distribution function. Now, if the probability distribution function of this random process, okay, this family of random variables, if the probability distribution is independent of where we look in time, then we say that the process is stationary. Okay? Now, stationarity is extremely important because we normally assume that the processes are stationary in order to be able to do the computations that we carry out. Now, it is possible to, and it's often the case, that we will talk about stationarity in what's called weak sense. So most of the time when we say that we are assuming stationarity, what we really mean in engineering often is that we are assuming weak stationarity. What that means is that what we mean by weak stationarity is this. Imagine that you cut here at time t1. And again, you don't have to mentally, you don't have to actually think in terms of physical things that you actually did 1 million, but at time t1, the process has a certain PDF. And so let's say that that PDF at time t1 was this, okay? Now that PDF will have a mean, let's say mean 1, and it will have, in this particular case, a standard deviation sigma 1. Notice that the fact that I say that there is a mean and a standard deviation does not mean that the process is a Gaussian curve. Any collection of numbers has a mean and a standard deviation, right? The mean is just the average of all of them, and the standard deviation is just each value minus the mean squared, summed together, square root, right? So any collection of these numbers has a mean and a standard deviation. Now if we take another time, the time t equal to t2, and we get a different distribution, I don't know, whatever, right? Mentally. So the PDFs at t equal to t1 and at t equal to t2 are not the same, let's say. However, let's assume that the mean of this one is the same and the standard deviation is the same. Then we say that this is good enough for us, we have weak stationarity. So when we say a process has weak stationarity, we are not saying that the probability density function is the same everywhere, but what we're saying is that the mean and the standard deviation, or more general, the mean of the process and the covariance function, when it's not just one variable, are not changing in time. Okay? Typically, we use the word just stationary, but what we mean is weak stationarity. Okay? By the way, in engineering also, it is common that we might do things like this. Here is an earthquake, the ground motion under some building. So the earthquake goes like this. Like that, right? And then it's very small. So obviously, this is not a stationary signal, right? In the sense that if we imagine a million of this, that could have been what's going on at the first few seconds or in the very end, just like in the drive here, is not the same as what's going on in the middle. But we might say that in this region of strong motion, the earthquake can be treated as being weakly stationary. So we would say if there was another one that could have been due to the same process, we would expect that the statistics as far as the mean and the standard deviation, no matter where we cut in time within this window, would have been the same values. Okay? All right. So let's see, that's random process, stationarity, ergodic. Ergodicity is a property that is that means the following. Let's say again that you rode the car one time and found this, right? So you rode the car one time for the 5 miles and you measured this at your sensor. If I asked you what is the PDF estimate of your random process, you're going to say, wait a minute, I need a few months because I have to do this drive 100,000 times so that I can take cuts across the ensemble to tell you what's going on. Well, most of the time we just don't have the luxury to do that. And so what we do is we assume, and hope that it is accurate, that the process that we're looking at is ergodic. If the process is ergodic, that means that instead of averaging down the ensemble, we can average along the signal to get the same result. So if I want to know what is the mean of the probability distribution, I can find the mean. Of course, I'm assuming stationarity also, but I don't need to find the mean by doing the realization many times. I just calculate the mean of the signal in time and I call it the same. If I want to know what is the standard deviation, I also, instead of having to have many realizations to know what is the standard deviation, assuming ergodicity allows me to say that looking through the right, I am just doing the same thing. So it's like saying, you know, you go a little bit to the right and that's the value here, and that's the value here, and that's the value here, and so on. So ergodicity means that you can assemble, that you can calculate averaging to the right instead of averaging down the ensemble. We normally do not prove that our processes are ergodic. We are just simply kind of forced by constraints of practical limitations to assume ergodicity, because that's the only way that we can practically operate. We just cannot collect a signal so many times to actually do the calculation down the ensemble. Okay? So that's ergodic. Now, let's talk a little bit about correlation, and let's see if I can help you not confuse correlation and whiteness and so on, and Gaussianity and whiteness, which is a confusion that often happens. Let's say again that we have a signal X from some random process, right? And it's this. So that's our signal versus time. Now, if I look at time t, and I look at time t plus tau, where tau is any number, right? I will have a value here and a value here. So let's say the value here was A and the value here was B, right? So at that one time t and at that tau, at that t and that tau, I got A times B if I multiply the two numbers, right? Again, if I am really literally doing this across the ensemble, that means that there is another one here, right? Another right. And then here, at the same t and tau, we will have C and D, and I could multiply it. And if I did that all over the place, and we took the average of A times B, you know, actually C times D plus all of those, right? Divided by the number of cases, right? So if we took the average of the product of two values that are separated a distance tau across, away, along the ensemble, down the ensemble, we would say that we have a correlation at time t with a lag tau. So I repeat, using again our 5-mile drive. This is one of them. There is in our head another 1,000 of them, right? We take a particular time, 3 seconds, 5 seconds, 1 minute after we started driving. At that time, we can cut down all our cases and we get a bunch of values, right? We also take a time a little bit shifted forward, which that shift is just tau. It's just something, half a second, 1 second, whatever. And we do that again and we cross down. For each signal, there will be two numbers. In this one I call it AB. On the next one it would be CD. B, you know, whatever. We now multiply them. Multiply them, multiply them, multiply them, multiply them. Add them all together and divide by the number of cases. The result would be the correlation at time t of lag tau. Right? Okay. Now, if the process is ergodic, we do not have to have all the realizations down the ensemble in order to find the correlation. We can do the correlation along the signal. So when we have an ergodic process, which is what we normally assume, then we say that the correlation, if the process is stationary and ergodic, which are our typical assumptions, then correlation is just a function of tau, not of t, right? So what we would say then is take any tau you want. Let's say that is a tau, right? And then take this and then move along, move along, move along, move along, move along. And every time you get, as you move along, you're getting pairs, 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 which are separated by tau. Average them all those multiplications out, and then that's going to be the correlation with lag tau, when the values are tau apart. Now, okay, so that is correlation. If you have a signal that is like this, I mean, this is almost a sine, right? Then it's quite clear, should be, that if you have a small tau, you're going to have a big correlation, right? Because imagine this tau, right? So when you multiply, this B and this A are quite related. It's not like this B has nothing to do with this A, right? So at a given tau, you will find that there is a very strong correlation here and so on, as opposed to a completely random signal in which what the value at a given point tells you regarding the next value is little. So if the correlation is equal to 0 for any tau, we say we have white noise. That is, white noise is the process, it's an idealization of a process in which the signal is such that knowing the value now doesn't tell us anything about what the value is next time. Okay? We are now at this point, right? And we know that this thing is a 7. And we are here. And I am covering the signal, so I don't know what's going on after this time, right? I know that now I am at 7. Now the next question is, what is, of course I'm talking in discrete time here in order to make some sense. So now I go my next delta t, what is the signal? If the signal is white, the fact that this was 7 doesn't tell me anything. It could be 22 or minus 15. Okay? As opposed to, of course, nearly sinusoidal, in which if I know it's 7, I normally have a pretty good idea that the next number is not minus 20, right? So this is what we mean by white noise. Now, A signal, this tends to be confused often, a signal that is random, okay, may be Gaussian. That means that when we look at a given, any slice, and we look down the ensemble, the probability distribution, that is the, not a probability distribution, the histogram of all the values that we get when plotted approach a certain PDF, right? And let's say in this case is Gaussian. In the case of white noise, that can perfectly be Gaussian. So the fact that the process is white noise does not mean that when we look down the ensemble at any given time, I do not see a Gaussian PDF. So it's perfectly fine to have something that is white and Gaussian, because I go down and it's a Gaussian distribution. However, if I look at the next one very close to it, it's Gaussian also, but knowing what the value was at t doesn't tell me anything about what the value was at t plus any shift. If the function is not white, then that means that if I know the value at a given time, I know something about the values that are coming after. Okay? Only in the pure whiteness situation, you know nothing. In the literature, people tend to use the word colored noise, okay, or pink noise, to imply that there is something that is random, looks like noise, but is not really perfectly noise, because knowing the values at some point does give you some information about what are the values coming after. Okay? Let's see. All right. Okay. Another concept that we're going to use in our subsequent methods to do damage detection is the idea of likelihood. Okay? We want to clarify what is the definition of likelihood. The term, the word, is pretty much descriptive, right? Let's say that you have a set of data. So the set of data that you have is, let me call it a vector, keep things simple, call it, don't call it a vector, call it just a x, which is, let's say, A1, A2, A3, A4. I don't need infinite of them, I just need some sequence. So I have this vector A1, A2, A3, A4 from some experiment. Okay. Now I do not know, we do not know, what is the probability distribution. Let's say that these are values that are sampled from something that is random, right? But we don't know. So we say, well, it may be from this distribution. Let's say that this is PDF 1. Or it may be perhaps from this other distribution. And let's call this one PDF 2. Let's keep the world simple and say that somehow we happen to know that those numbers are actually numbers that were pulled out, they were realizations obtained from a bag of numbers that actually was consistent with this distribution, or with a bag of numbers that was consistent with this distribution. We don't know. So how can we make a decision that is rational regarding which one is more likely? Well, we simply say, let's put A1, A2, A3, and A4 over here. And so we find A1, A2, A3, A4, right? So this is A1, A2, A3, A4. And we see that if this was the distribution, then the PDFs associated with 1, 2, 3, and 4 would be these dots, right? Let's call them P1, P2, P3, and P4. And let's say that those are the probability densities associated with the values here. Now, we assume that this A1, A2, A3, A4 are independent variables. That is, when A2 was pulled out of the bag, it had nothing to do with A1, and this one had nothing to do with either one, and so on. And that they were all being pulled out from the same bag, so we refer to them as being independent, identically distributed. So A1, A2, A3, A4, notice that you see them as numbers here, right? But remember that you want to think about them in terms of an ensemble going down. So this A1 just happened to be one of the numbers that we pulled out from a bag. This is another number that we pulled out, right? Another number. So each one of them could have been a different number, right? They are independent, and the fact that they are identically distributed means that they all respond to the same PDF. Now we define the likelihood simply if 2 as the probability of getting that sequence. Since they are independent, right, the probability of getting that sequence is simply the product of the probabilities. So we would say that the likelihood, in this case, let's call this case 1, is just P1 times P2 times P3 times P4. That's the likelihood. Now we come to this other one and we say, well, what about here? And we say, okay, so here is A1, here is A2, here is A3, and here is A4. So I put them up there, right? And we read on this plot what are the probability densities, and let's say that in this case they were, I don't know, Q1, Q2, Q3, and Q4. Since these are independent and identically distributed, we say that the likelihood 2 over here is just Q1 times Q2 times Q3 times Q4. Now, if we had to choose between which one of these two is the most likely correct distribution, it's natural to say, let's choose the one that has the largest likelihood, right? And that's what's called, in general, procedures that are carried out under the premise of maximum likelihood. So this is the likelihood of that data, if that were the distribution. This is the likelihood of the same data if this were the distribution. Now, likelihoods are normally very small numbers because each one of these probabilities might be a small fraction, right? Depends on the application. But as you start getting large data sets, the likelihoods will be very small. Small times small times small times small times small. If you have 100 of them, it gets out of control. And for that reason and others, it is much more convenient, instead of working with likelihoods, to work with the logarithm of the likelihoods. So if we take the log of the likelihood L1, right, you know that the log of a product is the sum of the logs, right? So that would simply be the log of P1 plus the log of P2, right, plus the log of P3 plus the log of P4, right? And if we were to do it here, we would have that the log likelihood for L2, the log of the likelihood L2, and now I will use the summation, is just simply going to be the summation of the logs of the QJs, right? And in this case, J goes from 1 to 4, okay? So as I said, for this reason and for other reasons, instead of working with likelihood, we tend to work with log likelihoods. Now, as a way into the next module, you can imagine that these numbers could be frequencies that we obtain at different times, or it could be something like that, right? And that these probability distributions may be distributions that we could postulate. If the system is not damaged, we think this is the distribution. If the system is damaged, we think maybe this is the distribution. And then we would say, well, given that data, which one is more likely, right? So that is where we're kind of going when I begin on the next piece.